So guys, just remember your assignment number 2 has been released. It's going to be the basis for your programming test number 2, right? So I'm going to give you the guide about 1 week before the test, but definitely focus on assignment number 2 and also number 3 as well. We'll also release that in time. It's definitely going to help to practice and redo, and then you should be okay, hopefully, for programming test 1. Okay. Anyway, so for your programming test 1, we already started the grading process. I should be able to run some initial processing for auto grading, and then I'm going to pass for basically submission that does not really compile. I'm going to pass them for manual grading to the TA, and then hopefully we can get things done. I'll give the result and feedback back to you, and there will be some regrading process for you to follow if you really believe there's some error. That's okay. But I will give them to you on Monday next week, the latest. I know it's a drop deadline next week, okay? And then whatever decision you have to make, you should have enough ground to really do it, okay? And then let's take a look at the semester calendar very quickly, right? It's also good to know where we are. We're definitely more than halfway, okay? Now we still got interesting materials to cover, quite a bit, okay? Okay, so we are now right here. March 2nd, right here. And your next assessment will be basically for this week and next week. There's no assessment, right? Your written test based on E-class, I'll give you more guidance about exactly what you can expect. It will be on the 19th of March, but most likely it's going to cover from the beginning all the way until March 12th, tutorial number 8, most likely, right? So for those of you who may want to get started preparing for that, I would say also take advantage of this written test. It's like preparing about part of your final exam as well. The format wouldn't be the same because for written test, you'll be on E-class, but for exam, you will be on paper. But coverage will definitely overlap. It definitely wouldn't hurt if you try to, excuse me, to actually start studying for that, right? All the materials will be covered as well, all right? And then, programming test number 2, its schedule will be on the 26th of March. Right? You definitely got enough time to really get to actually understand about the materials for implementing graphs in Java. Okay. Any questions? All good? All right. Sounds good. So today the plan, I want to finish off the final small number of properties about comparing depth first search and breadth first search. I think that can also help you on the written test and programming test as well. So we'll talk about it, and then we should really start a new topic, which is about weighted graph and shortest path algorithm. It's going to be very interesting, a very classic one. So we're going to study from every aspect for that particular algorithm, right? We'll have some introduction today, and then we'll see many things later as well. Okay. Let's now do a very quick recap as usual. Okay. So last Wednesday, we talked about, all right, that's like a programming tip for your assignment number 2, right? Just make sure that's kind of 20-30 stuff. Just make sure you can read about test cases involving exception, right? It's kind of important for you to really read the test cases. Of course, it's going to impact later assessment as well, okay? If you got any trouble, do let me know. And that's a visualization about the edge list strategy. So that will be the first one we're going to do in detail. But I think for the other 2, we may not necessarily do in assignments. But I think once we talk about visualization, you can do very similar programming, like a coding task as this one here. But just focus on assignment number 2. And this visualization, hopefully, is going to help. Especially pay attention to, for every vertex, we have a pointer going back to where they are in the list of vertices. So this is going to make removal of vertices constant time, big O of 1. Similarly, you can see for every edge objects, they also have a 1 pointer back to where they are in the list of edges. That's also going to make removal of edges efficient. All right, so these are the 2 points you want to definitely note, right? And see how you can program accordingly, efficiently in your assignment number 2. Okay. Good. And we spoke about breadth first search, right? It's basically a level by level. You can the tree that we can get from doing a breadth first search. We also, you can say it's a spanning tree, but also we say it's a level tree. That's something I'll write down a little bit later. Okay. So you start from here, and then you just go level by level. Level 0, level 1, level 2, level 3. Of course, graph in general may contain cycles, in which case you might get not just discovery edges, but also you got cross edges. Okay? So that's just the first example we did, just to make it simple enough. But in general, you should expect there might be some cross edge, either go this way or go to the next level, right? That's something we saw last time, okay? And then we talk about two kinds of edges, either discovery edge or cross edge, okay? No forward and no back, okay? Only cross edge. And that's the example we did. In class last time, we did one here. We only did one, okay? And I think Diago maybe also asked me about how we can divide levels if we got a different start vertex, right? That's something you guys can do as well. And I will definitely encourage you guys to also do this one as well. I'm pretty sure, well, I cannot say 100%, but almost certain. In your written test, that's gonna happen about 2 weeks later, you will be given a tracing question like this, either directed graph or undirected graph or both, right? On the breadth first search, depth first search, anything that we kind of did in class, you should really expect them, might be there, okay? But I think this one is very good preparation, right? You can also see the solution on the lecture side. There's a link for the video, right? Take about 25 minutes or so, but you can fast forward. That can make it half the time, okay? So breadth first search is pretty straightforward. We don't have to worry too much in the class time. All right, and then we started talking about different properties, especially we talk about depth first search and breadth first search both together, okay? So time complexity. Any algorithm that's going to be based on depth first search or breadth first search, we'll see as we go, right? For example, topological sort that we're going to see later is based on depth first search. And the running time usually will be proportionate about the number of vertices and the number of edges in your graph, so depending on how many you have. And we have a special case where if your graph is rather complete, the number of edges is really reaching its maximum, which will be n squared, right? It's like a complete graph. All right, and then, of course, the insight will be for depth first search, we talk about push and pop. For breadth first search, we talk about InQ and DQ. So for efficient algorithm, you should really do push and pop, also InQ and DQ exactly once for each vertex, okay? All right. So guys, any questions about this? Right, we kind of cover the fundamental way to traverse the graph, and later on we're going to see how to use this kind of a traversal for different algorithms, at least one or two, okay, to see the idea. Okay. And then we spoke about connected components, right? So let's say this is one graph, undirected, and then this graph is not connected. We got connected component number 1. We got another connected component number 2. If you start from a vertex in this particular connected component, what depth first search or breadth first search can guarantee is the tree, the spanning tree is going to create, is going to span over just this particular connected component that contains the start vertex. That's what we can guarantee. So pay attention to the wordings over here. It's very precise, right? So if you only start from here, for example, from vertex A, or even if you start from vertex B, you can only reach out to all the vertices in this particular connected components, but not anything else. So that means, I'm going to talk about it as well today. If you already know you got a single run of depth first search or breadth first search working, how can you find out all the connected components? You need kind of like a loop structure. It's very straightforward to write, right? But I'm going to write it together with you, just on the paper, okay? All right. All right. All right, that's for last time. No questions? Okay? All right, good. Okay, so today, let's now talk about a few more properties, right? Let's start with, I think your fellow student is not here today, but the other day, at the end of the class, I kind of asked him to really describe the steps about figuring out the number of connected components, right? So for example, let's say for this one here, if I want to use depth first search, the first depth first search will find out these connected components. The second one, if I start from here, I'm going to find the second one. 1 and 2. I got 2 connected components. I can also try maybe breadth first search. If I start from here, the first run is going to cover this. And the second run is going to cover this, right? You can use either one. But normally you don't mix. You don't want to say, oh, for the odd iteration, I want to use depth first search. For the even iteration, I use breadth first search. Well, it's okay, but it's not common. Okay. Why don't we write a little bit of pseudocode? Not exactly pseudocode. Write some loop structure. I think you can also find some insight there. For simplicity, we're only considering undirected graph. So there is one important property missing out, which I decided to go a little bit later, okay? Which is about whenever you're trying to do your breadth first search or depth first search or breadth first search, depending on if there's any direction in the graph. In the case of directed graph, things will get a little bit more complicated, but I'll talk about the complication a little bit later. For now, let's make it simple. Directed graph, sorry, undirected, as you can see here, all right? So now let's say here, how do we figure out just number of connected components? Okay? Let's have some assumption here. So let's say assumption is the input graph may or may not be connected. We simply don't know. If I tell you that it's already connected, you don't even need a loop. Just one single DFS or BFS should do. But the assumption is we simply don't know. The input graph may or may not, may or may not be completed. So how do we run the fragment of code? So we're assuming that we already implemented depth first search, like from your assignment number 2, right? All right. So let's now, well, I'm just going to show you one way. If you got different programming preferences, you can do that as well, right? Let's just do one way, okay? Let's say we have a counter. I can say some integer, let's say number of vertices visited. Just on counter. Well, if you like, actually, let me make it a little bit shorter. How about just say count? And this counter here is going to keep track about the number of vertices visited. So the idea is we want to keep doing depth first search or breadth first search consistently as long as there are more vertices to be discovered. Got to keep doing it, right? So at the end of each iteration, you should really check to see, have we achieved that particular goal, all right? So we can use a while loop. So while, okay, I'm going to leave this particular condition here as a placeholder for now. We can figure out a little bit later, okay? And the body of the while loop is going to be, the big picture is very clear, right? We're going to keep doing, let's say, depth first search. You can change that to breadth first search if you wish, okay? You can say you want to somehow, first of all, you want to pick some unvisited vertex X. Okay, it is very important to know that it's unvisited. Okay, pick one, doesn't matter. For example, let's say here, if I start doing a depth first search from here, I can pick this one, I can pick this one, etc. Right, just in the beginning, right? And then we're going to do a depth first search on that particular unvisited vertex that's picked. So we're going to do right here DFS, for example, and then X. And there's an important assumption here. The depth first search routine or method itself has been somehow extended a bit to keep track about how many vertices it's going to visit. It's going to increment basically the counter accordingly. Okay, I'm going to write it down, right? Okay. The count is updated accordingly. Just for example, we might start with the count being equal to 0. And then we start with A. We do some depth first search, for example here, okay? And then after that, 1, 2, 3, 4, 5. The count should be updated to 5. At this point, the counter value is 5. But how many vertices do we have in total? Strictly larger than 5. You can see there's another connected component to be explored. So now we know that the loop shouldn't really terminate just yet. We should keep going, right? Okay. So one thing that's also important is very important observation. How many times the body of the loop, the number of iterations should just correspond to the number of connected components we have in the input graph. So you can think about iteration number 1 is going to cover all the vertices in these connected components. Iteration number 2 is going to cover all the vertices right here. So what's left is right here. Should be quite straightforward, but can anybody suggest? We're basically saying as long as the Boolean condition is true, we should keep repeating the process of picking something that's unvisited and also do another depth search from that pick vertex. So what should I put as a Boolean, Barbara?
Well, the count doesn't equal to the total number of...
Does not equal to?
Doesn't equal to the total number of...
Vertices. Okay, that's good. I like it. That's good. All right, that's correct. Exactly. And then I'm going to go a little bit further about some logical reasoning. Okay. So here, what Barbara said was exactly correct. So we're going to say while the count is not equal to the number of vertices. Of course, you're going to find out if there might be some attribute, there may be some helper method for you to figure out the number of vertices. We can simply go to doubly linked list of the vertices and see what the count is, right? That one you can figure out. And it is so important to see why this is important, right? So let's look at just this condition here, okay? This condition right here. So this one tells you that as soon as the condition evaluate to false. In this case, the not equal to evaluate to false means that equals is true, right? That means we reach just equal to all the vertices. Now it's time to exit without wasting any more resources to go any further, all right? So here it will be not the case, count not equal to the number of vertices, all right? And of course, this condition here, you got double negation. Okay, so this is equivalent to the count exactly equal to the number of vertices. That's exactly what we call the exit condition. So that's a condition for you to exit from the loop. Let me finish this and I'll take a question. Yeah, give me one moment. All right. To false, that means all the vertices are visited. Okay, let me write better. Yeah, question, please. Yeah, it will work as well. Yeah, I think, yeah. So Jada suggested another possibility, which is totally fine. Okay, I can suggest that. So let me just say star sign here. Alternatively, you can also write, for example, the count strictly less than the number of vertices, right? That's also fine. Because we know that when we exit when the count is what negation of smaller than should be larger than or equal to. But in our case, we shouldn't really allow the larger than to really happen. There might be some little bit more reasoning you have to do. So I personally prefer this one here. Yeah. But that one is fine too. Yeah. Okay. So you can expect your programming test number 2 will be around this kind of flavor. You might be asked to maybe partially or totally to implement depth first search or breadth first search, which should be very routine. Just make sure you practice before the test. But I might give you some novel graph question to figure out. For example, I'd say, now given that you got your depth first search, implement another method, given a graph, how can you figure out the number of connected components? So you're going to call your depth first search as a helper method and do some loop around it. Right? So that might be some extra code you have to write. That'll be the flavor for programming test 2. Okay? Questions? Okay, okay. Let's now move on. And then the next one here, just about quick, about spanning tree. That's really something we said already, okay? So here, what I want to say is right here, so a DFS or BFS gives a spanning tree. A spanning tree of the, again, connected components containing the start vertex. Okay, let's see two examples here. So this one here is depth first search, right? If you look at that, this part here, all the discovery edges, right? This part over here, it forms the spanning tree of the connected components containing A, because A was the start vertex. Right? There's something we kind of said earlier. I just want to make it more explicit. Right? Of course, if you count the number of edges in this spanning tree, it should be number of vertices minus 1. Right? Again, a property we keep saying, keep emphasizing. Similarly, if you look at this one here, using breadth first search, right? Just go level by level. So if you look at all the discovery edges over here, right? So this one here is also a spanning tree. It's a spanning tree of the connected components containing, again, start vertex A. For undirected graph, it doesn't really matter how you pick the start vertex. You can always reach out to everywhere in the connected components. But in the case of directed graph, it will be a little bit more complicated. We'll talk about it a little bit later, not today. Okay. Okay, so one more thing to say. The spanning tree, in the case of depth first search, is called a DFS tree. Right? That one is obvious. And in the case of breadth first search, you can either say it's a BFS tree or a level tree, because you simply divide the tree nodes into different levels. Level 0, level 1, level 2, right? It's a level tree. Okay. All right, questions? Okay, okay. Let's keep going. Okay. The last property before we spoke about how you can adapt the depth first search and breadth first search, and then we should be ready for a new topic, right? Two more things, okay? Okay, this one is important about cycles, okay? Let's kind of revise about what we know already, and then we'll summarize that in a table, and I'll give you an example. Let's now talk about directed graph and undirected graph. Let's say for undirected graph, when we do depth first search, we can either get discovery edge or back edge, right? For undirected graph, when we do breadth first search, we can either get discovery edge or cross edge. That's good. Now, directed graph. If we do depth first search, what edges do we get? Discovery, back, cross, and forward. Okay? And for breadth first search on directed graph, we also get the same two kinds, also discovery edge and cross edge, right? So these are the four possibilities, right? You want to be very familiar about like when to consider what. So now we are talking about, let's say you're doing your breadth first search and depth first search. And let's say now, for example, now I'm doing a depth first search on a directed graph. Now I can find that the edge I'm currently considering is a back edge. Can I conclude right away this is a cycle? The answer is yes, first of all. Okay, I'll summarize. Another example. Let's say I'm now doing a breadth first search on a directed graph. And now I'm discovering something like a cross edge directed graph. Can I conclude right away this is a cycle? The answer is you cannot. So there are different possibilities we have to think about. Right? Let's summarize this in a table. Okay? And then we'll see example. Okay? Let's enumerate all the possibility here. Okay, that's good. And then, okay, for the first dimension, let's consider about the whether or not the input graph is directed or not. Okay, so about input graph, it can be either undirected or it can be directed. And here's a critical question we'll want to ask. Does there exist a cycle? Okay. Okay, we're asking the same question here. Does there exist a cycle? Well, we're asking if the graph is acyclic or cyclic, right? Similar question. Okay. And we're going to talk about all the possible edges. Okay. Discovery edge, we don't have to worry. Discovery edge can never tell you that it's a cycle. You're just discovering new vertices. It's only when you are visiting something that has been visited before, there's a possibility, right? And then we'll talk about the edges right here. And also the traversal. Okay, let's divide them into 3 columns. Okay, column 1, column 2. Okay, I think I can make it a little bit better. How about this? Okay, that's good. And for breadth search, we only have to consider cross edge. Okay, anything that's not discovery, basically. So for breadth search, we talk about a cross edge is found just now. Okay? And then for depth search, it depends. If you're doing a depth search on an undirected graph, you can only have back edge. That's not discovery. But in the case of directed graph, you may have all the other 3, right? Okay, let's distinguish between them. Let's say you got depth search. Either a back edge is found versus when you are doing the depth search, you have found either a forward or a cross edge. You're basically asking the following question. If I actually run into any of these scenarios, can I return true to say there is a cycle right away? That's really the question we're asking. All right? Some of them, yes, you can. Some of them, you just cannot. Let's summarize the result first, and they'll give you some intuition. Okay? All right, so in the case of depth search, and whenever you have found a back edge, which means you kind of point back to the ancestor, either in the undirected or directed case, always you can say, yes, there is a cycle. All right? So this one here, I'm just going to say, yes, there's a cycle. Doesn't matter if you're doing depth search on directed graph or undirected graph. Doesn't matter. If you found a back edge, this cycle. All right? And for forward edge and cross edge, first of all, for undirected graph, they are not applicable. We never try to find out forward and cross edge when it's undirected, right? So for this one here, we can say it's not applicable. Okay? We don't even consider. Okay? But in the case of directed graph, if we have found a forward edge or cross edge, it turns out you cannot conclude right away there's a cycle. There might be that you can find by other back edge, but not just by finding the cross edge or forward edge itself. You can conclude there's a cycle. You just cannot conclude it. Right? So I'm going to say not necessarily. Okay, we're going to elaborate using some example. Not necessarily. All right. And about breadth-first search, situation a little bit simpler. Okay. If we're doing a breadth-first search on the undirected graph, if you got a cross edge, maybe either between two vertices at the same level or going to another next level, either way. All right, that's already like a vertex that's already visited. All right. In the case of undirected graph, yes, there is a cycle. But in the case of directed graph, again, not necessarily. So direction is going to add some complexity for our consideration. All right. So this one here, not necessarily. Okay, for these two. Right, so this table basically summarizes what you're supposed to know, but we're going to see some example, okay, to convince ourselves. All right. Right here, let's talk about undirected graph first. You can see here we got undirected graph and also undirected graph, right? And then we do depth first search, we do breadth first search. Right? I'm also going to do partially. Okay? As soon as I can identify a back edge, I can conclude right away that there's a cycle. Okay? So for example, let's say in the case of the depth first search, start from A to B, and then B to C, and then C to A. This one tells me I have a cycle. And I basically can somehow manipulate the vertices that's already in the stack and figure out the path to lead to that cycle. Right? That's something you can try to practice. Okay? So this one here is a cycle. This part here is a cycle. Okay? And let me write a little bit more. Okay? That can give you a little bit more inspiration. Okay? So the path leading to a back edge denotes a cycle. A cycle. So we talk about back edge, and it represents a cycle. Okay, like that. Okay, let's look at the breadth first search as well, also on undirected graph. So you can think about for these two, we got undirected. And also here, we got undirected as well. Okay, these two. And for breadth first search, let's see how we can find out maybe some cross edge. Okay? For example, let's say we start with A. First of all, you reach out to all the adjacent vertices, A to B, A to C, A to D. Right? And then for level 1, for level 1 here, we start with B. That's the front of the queue. You can either go for BA, but it's already there, but BC, right? It's a cross edge. And this cross edge also suggests that it's a cycle, right? Because you can see go from A to B, B to C, C to A. There's a cycle. Okay. Okay, also this part here is also a cycle. Okay, this one here is also a cycle. When identifying a cross edge. Okay. Okay. All right, we got two more diagrams to talk about. Actually, I'm going to create a fresh one because I realize I shouldn't overlay too much. Okay, let's talk about breadth first search first. Let's say now we have this graph here. We got A, B, C, D, E, F undirected. But now let me introduce directions, some arbitrary directions to it. Right? So this is a directed graph. Now we want to show that discovering or identifying a cross edge itself may not suggest right away there's a cycle in the graph. Maybe you can identify a cycle maybe later, but not just by the cross edge itself. Okay? Okay, so here. So what we do is A to B, A to C. Right, you can see here, we don't really do A to D, right? Because there's no such direction to go from A to D. Right? So only A to B and A to C. Level 0 and level 1. Okay. So think about, here we got level 0. And this part here is level 1. That one there is level 1. Okay, good. And then here, from B here, B to C, right? That one is also a cross edge because it's going to a vertex at the same level. That one there is a cross edge. However, just this cross edge itself cannot really find us like a cycle path, because if you go from A to B, B to C, you cannot really go from C back to A. Not really. So the cross edge itself does not really prove this is a cycle. There might be other ways to really prove it, but that's for later. Okay? Okay. So I'm going to write something down here. So here we got this part over here. So cross edge does not imply in general a cycle. All right, that's for the cross edge. And actually very similarly for depth first search as well. Very similar, but I'm going to just show to you very quickly. Okay, I think I can keep the same diagram. That's okay. Okay, so now for this directed graph, let's now try depth first search. Okay. And of course, we're going to get 3 kinds of edges, right? That's not discovery. Okay? So here, I got A to B, B to C. Okay, I'm just going to skip some steps a little bit, but you guys can also double check for me, right? Let me know. But the idea is really there. Okay? Let's say these are the discovery edges over here. Okay? So far. And then, when I do A to C over here, and when I go from D to A, and I can also go from F to D, like that. Right? So all these three green edges can be categorized differently according to our depth first search. Before, I'll let you double check. Okay? The one that's going to suggest there is a cycle is right here. So this one here is a back edge. All right. So the way we're going to find it would be A to B, B to C, C to D, and then D to A. So this tells me about the witness for a cycle, back edge. Okay. Let's write that down first. Okay. So this one over here, back edge, which represent a path to go from A and then B and then C and then D and then A, right? That implies a cycle. The other two, not necessarily, because this one here is actually a forward edge, right? You can see here we got A to B, B to C, and then A to C. That closing there is not really a cycle. Right? You really rely on the back edge to find the cycle path. Okay? So this one here, not really. And also this one here is a cross edge. You can also double check later. This is also a cross edge. Okay? If you look at the cross edge, let's say for example, A to B, B to C, and then C to F, and then F to D. But you don't really go back right here, right? So the cross edge is not really also going to find you a cycle as well, either. Okay. So the main thing to see is for these two instances, okay, I'm going to write it down here. This one here and this one here. A forward edge or a cross edge also does not imply, in general, a cycle. You really want to rely on the back edge itself. All right? So this example here just corresponds to the table we have right here, right, about a different scenario. Okay? Try to create maybe a different graph yourself just to convince yourself. Okay? Guys, question, please. We got one more, and then we can move on to a new topic. One more. Okay. Yeah, think about these kind of issues here. We covered quite a bit about graph, right, so far. You definitely want to, if you have to catch up, or you have to make sure you study for everything deeply, so you'll be ready for the written test about 2 weeks from now. Okay, final bit. It's really about depth search and breadth search. So these are the very fundamental ways to systematically traverse over all the vertices and edges in the graph. And there are many questions that has very practical implication that we can actually use these two traversal mechanisms to answer. I'm just giving you the most common ones. All right, let's talk about each one of them. So here, question number 1. I want to find a path between two vertices. If there's a path, return that path, maybe as an array list. If there's no such a path, return null or empty list, something like that. Any suggestion? Just hand wave a little bit, that's okay. This one here, you will do either by depth search or breadth search in a very similar way. You can choose either, whichever you feel more comfortable. But the question really is, how do you find specifically between U and V? Little hints. Is there a path between B and E, for example? Obviously there is. You can see it from the diagram. But algorithmically, how do I find it out? And I want to return one path as well. Yeah, go ahead. You traverse everything, right? Okay, that's good. So now, let's say you do use depth search. If you want to commit to one depth search, what's going to be the start vertex? Do you start with arbitrary vertex? U? You're suggesting that, let's say I want to find between B and E. You might start with maybe a depth search from B here, and then you want to see throughout the course of one particular run for the depth search, can you ever reach to E? If you're able to, that means it's reachable. All right? Good. Okay, so let me write it down here. Give you some rough step. Start a depth search or breadth search from one of the m vertices. Let's say U. From U, okay? And number 2, you basically just let the depth search run, and then you have to add an extra if condition maybe somewhere, okay? You want to say if V is reached, then there is a path. All right? And how can you figure out exactly the path? You may want to look at a stack, or you want to maintain a list. You can do either way. Okay? I'm going to give you a little bit of hints here. Number 3, to return the path. Okay? Either you can maintain a list, like an extra variable, like an array list, or maybe linked list, whatever you like. Or you can simply somehow look at a stack if that's possible, right? I'm leaving that a little bit vague for you. That's something you really want to dive into, okay? Or, number 2, use the stack. Okay? Okay, number 4, if you never reach U, starting from U, you never reach V. That means they're not really reachable to each other. There's no path. Okay? Could be that I want to find a path between A and I. Starting depth search from A, I will never be able to reach I, right? So there's no path. If V is never reached, okay, you can say return null. Yeah, Just a bit of Java, right? Null, or maybe empty list, whichever way you like. Okay. All right. This one here, basically identical question. This one might be even simpler. I'm not even asking you to really return a path, just true or false, right? Okay, so is U reachable from V? Okay, so you can say start DFS or BFS from V. As soon as U is reached, return true. Return true. If you never get a chance to return true and you have visited all the nodes, then return false, right? That's the idea. All right. This one here is pretty much covered, right? So if you remember what we did earlier over here, right here, let's look at the code here. This one here calculates about how many connected components we have, right? Similar, okay? But now, here I say all the connected components of G. This one is slightly more sophisticated, right? First of all, how do we represent each connected components, right? Well, it really depends on the Java implementation, okay? Let's say, for example, let's say each connected components, right? This will be connected components number 1. This will be connected components number 2, right? Let's say, whenever I want you to return a connected components, it's going to return basically the spanning tree that's going to cover all the vertices, okay? So, for example, is represented by the spanning tree, okay? For example, I'll just put it here. Let's look at this particular connected components, right? That one there is going to be connected components will be, first of all, we got A, B, C, D, E. So we got A, B, C, D, E. All the vertices, A, B, C, D, and E. And then spanning tree is going to be A, B, B, C, C, D, and C, E. We don't need to include anything that's not discovery edges, just the discovery edge, right? That one there is going to be A, B, and then B, C, and then C, D, and then C, E. Okay? Or it could be just as easy as I just want you to return just the edges. That's going to form the spanning tree, right? There's some flexibility. Depends on how I set up the JUnit test cases, okay? This might be something we can try to practice, maybe either before the programming test too, or maybe in the assignments. I'll keep that in mind, okay? What kind of data structure can you use for this, for example? You can use array lists, for example. That's definitely a collection. But here, since the order of the edges doesn't really matter, so it might be more appropriate to use maybe a hash set, for example. Right? So there are different possibilities over here. Okay? Okay, so I'm going to write by the spanning tree. I'll give you a little bit of note hints over here. What you do is run multiple depth first search or breadth first search. Each run I don't seem to see anything.
What is it called? The adapter?
Adapter.
For HDMI?
I don't see it here. If I do see anything, I'll put it here.
Okay, thank you.
No worries. Okay, sorry guys. So over here. So each run for the DFS or BFS, you just have to, whenever you see a discovery edge, you're going to add them to the set, basically. Okay? Each run will accumulates the discovery edge. Discovery edges. into a set. Okay, that's for a particular spanning tree. But if you got multiple spanning trees, you put it in an array list, or maybe a set of sets, right? So the different ways you can do it. So guys, kind of idea is possible, right? For you to imagine, right? You basically run multiple DFS or BFS for each one of them. You just have to make sure put all the discovery edges into a particular set. And overall, if you got, let's say, 2 connected components, you got 2 sets in total to be returned. You can put those 2 sets into an array list, for example. Okay. Right, compute a spanning tree. Well, that one is actually simpler because you just want that particular one, right? Okay, compute a spanning tree of a connected graph. So here we are assuming that the graph you're given is already connected. So we just want to return the spanning tree. So just run one single. So only a single DFS or BFS will be required. And we're using the similar idea. You're still going to represent a spanning tree by all the discovery edges. So only a single set should be, will be enough. Okay? Now, is the graph connected? Anybody? Because we're getting there, and we should really take a break. It's been a little bit longer than usual. Given a graph, I want to return true or false if that's connected. What should I do? How many DFS do I need? Do I need multiple DFS? Jada, you said no. So how do we figure out? Yeah, exactly right. So if you run a DFS or BFS, if somehow you cannot really cover all the vertices by a single run, that means the graph is not connected, right? Good. Awesome. Okay, let me just summarize the essence here. So a single run of DFS or BFS. If all the vertices visited return true. Otherwise, return false. Okay. All right. So here, final one. How do we return a cycle? You basically want to figure out that back edge, right? So that's really the stuff we spoke about just right here, because only a back edge can suggest there's a cycle. So you want to focus on that back edge. So you want to, once a back edge is identified, infer the path leading to it. Okay, so my answers here are just to give you some high-level idea. So this will be something, might be some of them we are able to do for programming, sorry, not programming, we're able to do for assignment number 3. I did put something there. Anything that's not there, you may want to practice them before the programming test. That's also good hints for you. All right, so that's definitely something you want to do beyond what's really assigned to you. Guys, any questions? Okay, why don't we take a short break, right? I think you guys definitely deserve that. All right. All right, so as for the slides, I think we should now start a new topic. Slide number 54, I think we're going to talk about weighted graph today, just for you to see the concept, and then we're going to talk about the Dijkstra's algorithm. You may have heard about the algorithm before, but we're going to study that very thoroughly for this part of the course. Okay, so let's now get some background information about what weighted graph is and some important concepts for you to know as well. Okay, weighted graph. Okay, so it's going to be slide number 54 and 55 I'm going to talk about, right? And then we're going to use a graph right here, like a airline company, like a flight map, right? It's mainly the states, but we will see, right? Anyway, just for the idea. Okay. And we're going to talk about eventually how to compute algorithmically shortest path for weighted graph. Okay, we got to explain what weights really mean in this context. Okay. And by the way, even before I talk about the definition, you can see that this graph here is interesting because for the edge, unlike before, we simply put a name like O or maybe P and then Q, etc. It's not a name. It has some meaning there. We simply put some integer value. And somehow for this graph here, all the value happen to be non-negative, like a not negative basically. But there's certain assumption that we have to make for calculating the shortest path. But I'll get to there a little bit later. So what does that really mean? For example, you got San Francisco, and then you got over here, is it Orlando? No, it cannot be Orlando, sorry. So let's say you got, okay, San Francisco, you got Boston, right? So there's an edge between these two. It's 2,704 miles, I presume, or kilometer. Doesn't matter. There's no unit here, just a number, right? And given this particular graph, right, we want to somehow calculate, for example, if I want to go from San Francisco to Boston, there are multiple ways for me to really get there. I can either go for route number 1, I can go for route number 2, I can also have a direct flight, and among all the possible routes, I want to find the cheapest one, in the sense that it should really take the smallest amount of mileage for me to get there. Right? It's kind of like a shortest path. Shortest path, not necessarily about the number of edges for you to get from one node to another, is the smallest, but the weights added up together will be the smallest. That's something we want to pay attention to. And there's some very systematic algorithm for doing this. Okay? But let's just clarify everything I kind of just said. Right? So first of all, let's talk about weights on edges. So weights on edges. So the weights here is really representing like a cost. So the problem is we want to minimize the cost for our resources. Okay. So the notation goes like this, little w, and then we simply do two vertices u and also v. Right, so that's one notation you have to watch out for. Why do we need to use the notation rather than using concrete example? Because when we actually want to prove the correctness of this algorithm, we have to refer to graph in general. So that's why you have to use the right notation. So that'll be one of the questions you'll be given to solve in assignment number 3 later. Okay, for example, we say that the weights between Boston and Miami. Right, you can see from Boston to Miami here will be 1,258. And there's a very important assumption here. The weights or the cost cannot be negative because the algorithm that we're going to introduce, the extra algorithm, it cannot really work if your edges have any weight that's negative. So here is a very important assumption. The weights for any edge will be larger than or equal to 0. Could be 0, but may not be practical, right? You don't say from one city to another, the mileage is 0, right? But theoretically, can be 0. Non-negative. We will explain a little bit later about why this non-negative assumption. Okay, we'll talk about it. And then to really make it work, it is possible to use another algorithm if we want to relax this assumption. There's just another one, which we wouldn't cover in this course. But I can at least suggest the name for those of you who might be interested for future reference. Okay, assumption. Okay, right here. All right, so far it's about individual edge. We have a weights. Let's talk about the weights for a path. Okay. So we talk about the length or the weight of a path. And we also use the small letter W to write it. So somehow the W is overloaded for two different purposes, but they kind of related to each other. Okay? So the way to write it, it goes like this. You have W over here. Inside, you're going to give a path. And a path here is simply just a sequence of vertices. Okay? Let me use angle brackets to really represent a sequence, right? So a sequence over here. Let's say we got k plus 1 vertices. Index 0 and index 1, and then all the way to index k. Okay? Okay, that'll be it, right? So think about right here. Right here. This is like an input to the W, like a path. Okay? So here we got k plus 1. So this is a path with k plus 1 vertices. All right, by definition, we're going to use the little w that we just defined on the edge level. Okay, just before that, let's now also point out these two are the same letter. W here and the W here, all right? So they're somehow overloaded. Okay. Well, it should be no surprise. If I want to figure out the weights for a path, I just need to figure out all the weights for individual edges that's involved, right? And I'll give you one example in just one moment, okay? And then what we can do is, let's now try to split it up. It's going to be the weights from these two, V0, V1, plus the weight of V1 and then V2, all the way to the last one, which is going to be with Vk as a destination, from Vk minus 1, right, to k, okay? Okay. V, k minus 1, and V, and then k. Okay, add them up together, right? So you can think about we got V0, V1, all the way to V, k minus 1. Since we got k plus 1 vertices, how many edges do we get? Exactly minus 1, which would be k edges, right? Okay, just for this part here. So we got k plus 1 vertices, so we got accordingly k edges. Again, how can I tell? If I look at the indices, I go from 0 all the way to k minus 1. So k edges. Okay? And make it a bit fancier. Okay? You can use a sigma notation. And this sigma notation will also be very useful when you actually try to prove about the correctness of the algorithm, okay, later. So I can simply say sigma over here, okay, I would be 0 all the way to k minus 1. Basically, it will be from 0 all the way to k minus 1. And the weights of V index I and V index I plus 1. I'm just playing around with the symbols a little bit, okay? Okay, why don't we look at one example here. Let's say I want to go from Los Angeles to New York, JFK. All right, so these are the two M vertices for the path. One path would be, I can go from Los Angeles to, I'm not sure what this city is, but it's a city. And then go from here and also to here, and then go from here to New York. So we got two intermediate vertices, right? So, for example, the weights between LAX and then DFW, ORD, and JFK, okay? It would be the weights between these two, 1, 2, 3, 5, plus the weights between these two, 802, plus the weights between these two, which will be 740. Right, you get an idea, right? Of course, between two end cities, there are more than one way you can actually figure out the path. We want to find the shortest one, right? We'll see exactly how to do that. One moment, okay? All right, so far talk about the weights on the edge level and also on the path level, okay? One more thing to talk about, all right, guys? This one might be confusing, all right? Now we're going to introduce another notation here. It's with a little d. First of all, let me start with this. Out of all paths connecting two vertices, let's say U and V, because there might be multiple paths out of all those, we write little d and then U and V. Let me pause here right away. We have seen little d before. What was that? Anybody remember what little d is? When I say little d of some vertex, it's when we did discovery time, right? For that first search on the directed graph, right? Just don't get confused, right? So here you got two vertices there, all right? Denotes the, all right, minimum length or weight, right? Remember we spoke about the length and weight for a path, but now we're talking about a path with the minimum, okay? Among them. All right, let's get this definition here, okay? So we're already talking about this one here. Okay, little d, and then two m vertices. And what that means is about the minimum length and weight, which we defined earlier. Okay? Now we'll see example, and then we'll see how to calculate gradually. Not today. I'll just give you, we only got about less than 10 minutes. We can look at the algorithm a little bit. Okay. Okay. Example. There's one special case. We'll talk about between two vertices, right? For example, if I say, what's the shortest length, for example, between San Francisco and this city here? It might be just this one here. That's direct flight, right? For example. So what about, let's say, for example, if I have, let's say, for our city, YYZ, right? Pearson Airport. So now, what would be the little d between Toronto to JFK, according to this graph? It's simply not connected. So that means it takes conceptually forever to get there. You just cannot get there. Okay? D of UV equal to infinity. All right? If U and V not connected, it's a very important special case. The algorithm is actually going to start with this special value and then keep updating iteratively. Right? That's something we'll see in detail on Wednesday. Okay? But it's a special case you want to watch out for. All right, let's see example. Okay, quickly. So, for example, the little d, the minimum length or weights between YYZ, Toronto, and Boston, for example, there's no such link. So conceptually, infinity, okay? Plus infinity, by the way. All right? And also the minimum length between New York, JFK, and also LAX. All right? JFK and LAX. It turns out the path I gave to you is the minimum, turns out, okay? This one here is just going to be equal to the weights between, okay? I'm just being a little bit lazy here. So that's the path we just spoke about, okay, right here. Let's just pick one alternative path just to show that it's really the minimum, right? So for example, if I want to go from here to here, I could have chosen, let's say, for example, well, it may not be necessary, but for example, I want to go from here to San Francisco, and then I will go to Boston, and then I will go to here, and then finally, I will go to here. Right? I can take this route. Obviously, there's one possible route, but it's definitely more expensive, right? And that one there will be strictly larger than the weights between any other alternative. Larger than or equal to be more precise. Sometimes the minimum may not be unique. As long as you can give the minimum, that's okay. Okay? So this will be the star star. And star star will be just the one I gave to you on the graph, right? So get the idea. And of course, if you can imagine that for us to really calculate some small graph manually, you can maybe look at all the alternative paths between two vertices and figure out which one might be the cheapest. But with a graph with thousands of vertices, and also between two vertices, there might be multiple, maybe 10 or 20 kinds of different paths. You cannot just do it manually. You gotta have a systematic way to calculate it, and also efficient one as well. Right? So that's something we're gonna study. Okay, good. We've got about 4 minutes. How about just look at something, right? And then we'll definitely dive into it on Wednesday. So the algorithm we're gonna look at is called Dijkstra algorithm. So Dijkstra, he's no longer with us. He's a Dutch scientist. He's actually a very famous scholar and also practitioner for software engineering. For those of you who might be very interested in this kind of formal methods and also software engineering principle in general or discipline programming, you can look it up, Dijkstra. He got lots of scholarly work published for us. All right. Okay, Dijkstra's shortest path algorithm. Okay. Let's just just spend a few minutes. Okay. I can just mention one thing here. I think we can end a little bit earlier today. You will see that in here, remember in breadth search, we also use a queue. But the queue is a first in, first out queue. But here, the queue I set explicitly is the priority queue. All right, so now back to your 2101. You got different ways to, can anybody actually tell me, I'm gonna review as well. What exactly is a priority queue? How is that different from a first in, first out queue? Anybody would like to give it a try? Did you want to try, or?
I think, doesn't it kind of involve like a heap?
Well, heap basically is one of the most common efficient implementation for priority queue. I agree. That will be the second part I wanted to ask. You cannot answer that. But what exactly is a priority queue? What kind of operations or property do you care as a user?
Doesn't it have like a key and a value?
You definitely, yeah, so it's going to be a collection. And in the priority queue, every entry is going to be a collection of entries. Each entry got key and value, yes. Okay, that's good. We got key and value. But what's so special about key and value? How do we operate on the priority queue? Whenever I want to extract something from the priority queue, what exactly do I extract from there? Yeah, so I can, for example, priority, so the lower the key value, the higher the priority. That's something we can learn in 21. I'm going to review, don't worry. Okay, so guys, yeah, we got 2 minutes. That's good. Okay, priority queue. So here, the key right here is going to be of some value. I will just say capital D value. It's capital. So on Wednesday, we're going to distinguish between lower d, which we just set in the definition, and also capital D. They have some distinction between them. They're related, but not exactly the same. Okay? The key is going to be capital D. And also, we basically have to do minimum key extraction every time. Okay, and then priority queue, conceptually, that's all we need to really understand Dijkstra's algorithm. However, after next week, I'm also going to distract us a little bit. I want to review about how we can use a heap to really implement priority queue, because the running time also depends on that. So we're also going to do that. Okay, so to implement, we have to use the heap data structure. And let me say one more thing. And when we talk about a heap, there will basically be two operations, either insert or delete. And whenever you insert or delete, you have to make sure you kind of maintain the properties for a heap. It's something called up heap bobbling or down heap bobbling. Maybe something you have done before in 2101. Hey, let me write it down, and then we're good. Okay, it's going to involve up heap versus down heap bobbling. All right, I'll stop here, and then on Wednesday, we're going to see Dijkstra's algorithm in detail.